Hello. The chair is blocking your path, so you can go this way. All right. So, good morning, everyone. Welcome back to Comp 330. So this is our final lecture. It's lecture 26. And it's, of course, being delivered. Hello. Oh, Dashiell is here. Wow. For the first time in a while. Yeah. You're going to have to, yeah, maybe you can walk behind me. But then you'll be on camera. Oh, no. Right. So as I was saying, it's this lecture is going to be delivered slightly differently than most lectures, because I'm going to deliver it with the Blackboard. That's why there's stuff already on the Blackboard, and I'm recording it with my phone so that people who aren't here, of which there are many, will be able to watch it. Okay? So as people are quieting down, Benjamin, you're quieting down. Oh, thanks. I'd like to give you today's and really the semester's final Italian expression. I would be remiss if I didn't give you an Italian expression on the last class. So today's Italian expression is the following. So it's un pezzo di pane. Un pezzo di pane. The literal translation of which is a piece of bread. You know, so if an Italian wants a piece of bread, they ask for un pezzo di pane. But the actual figurative meaning of this expression is to say that someone is a good person. Okay? So now, what's an example of a sentence in which I use this expression and it's relevant to you? In this case, it's very relevant. Cesare, that's me, is extremely fortunate and extremely grateful to have had so many pezzi di pane in his 330 class this semester. So I said pezzi and not pezzo because the plural of pieces is pezzi in Italian, and I'm calling you all good pieces of bread. Okay? So that's today's Italian expression. For slightly more serious announcements, I just want to remind you that assignment 6 is due tonight. And this is a hard deadline, so I've already received some requests for extensions. I cannot grant extensions, so please do try to submit it in time. The other thing I want to say, just in terms of the final exam, is that the review session, in case you missed it, is going to be this Friday, December 8th, I guess. And it's going to be, what did I say, 1 p.m. to 4:30 p.m. in MC 204. Okay, and I also have extra office hours. I posted the extra office hours on myCourses under the final exam tab on myCourses. The other thing is that I'll post the final exam review guide hopefully by the end of the day. So there's the review guide, which I highly encourage you to consult, because there'll be details for how to prepare for the final, which is pretty important, and also some review questions, some of which I'll solve during the review session. Okay. The other thing I want to talk about quickly is the Mercury course evaluations. So the last time I checked, the Mercury course evaluations were at a whopping 12%. So that's like 30 students out of 250. And now, at this point, there are 30 students here, so I can't really ask for more. So people watching the recording, please fill out your Mercury course evaluations. Actually, what I wanted to do is to encourage you. I wanted to give you a few sort of bonus marks on your final grade to encourage this. And then I asked the department chair, and he said, no, you can't do that. So please just do it, because I'll actually read through all of the course evaluations, and I'll take them to heart, like I did for the sort of midterm evaluations. So maybe my handwriting is better on the Blackboard, so that shows you that I'm working on it. Okay? And the other thing, in addition to the sort of Mercury course evaluations, I'm not sure if you've heard of this website. It's called Rate My Prof. And I've taken the liberty of adding myself on Rate My Prof. So if you'd like to, please add a review there. It can be brutally honest, and I think what I'll do next time that I teach is I'll read some of the reviews at the beginning of the first lecture, so then people will know what they're into. Okay. The last thing I wanted to say is I wanted to take a picture with everyone at the end of class, but there's not many people, so maybe I'll do that, maybe I won't. We'll see. I have a guest student here who can take the picture for me. So, and that's it with the announcements. So I can take questions about the announcements. Louis? Yeah? Oh, yes, that's a good point. Oh, the course evaluations are due tonight. They're tonight at 11:59 p.m. Yeah, great. Okay. Thanks for the question, Louis. Okay, very good. So now we can move on to the actual material of today, unless anyone has questions about admin. No? Okay. All right. So now I have to erase all this. All right. Okay, so now watch me erase. Oh, by the way, I don't think I mentioned this. The reason why I'm giving the lecture on the blackboard is because I'm using this chalk, which is very expensive, and it comes from Korea. It used to come from Japan, but now they make it in Korea, which is fine. Okay, so the topic for today will be about reductions, your favorite topic in this class. But it will be about a slightly different type of reductions. It will be about Turing reductions. But before we talk about Turing reductions, I think what I'd like to do is I'd like to review quickly mapping reductions or many-to-one reductions. Okay, so recall mapping or many-to-one reductions. Reductions. So in mapping or many-to-one reductions, you're given two decision problems, P and Q. Right, so P and Q are decision problems. Okay? And what you want to show is you want to show intuitively or at a high level that Q is at least as difficult as P in sort of a mapping reduction manner. Right? But so what this really means is that so the goal is that if you can solve Q, right? There's a decision procedure to solve this decision problem Q. Then you can solve or decide P, right? So this is what a mapping reduction is at its core, and this is what reductions are in general. You have two problems, and when you say that P reduces to Q, this really means that if I have a solution to Q, if I have a solver to Q, then I can also solve P with that solver. Okay? This is what a mapping reduction is. And in particular, a mapping reduction has sort of a certain protocol that you're supposed to respect when you do it. And so it follows two steps. So the first step, right, which is sort of similar to any other reduction, is you want to convert. If you're doing, P mapping reduces to Q, you want to convert an instance of the decision problem P to an instance of the decision problem Q. And here, the instance of P is arbitrary. And here, the instance of Q is particular. It's a particular instance, which is designed as a function of I sub the decision problem P. Okay, so you want to convert this instance of the problem P to an instance of the problem Q, right? But you're doing this in a sort of constrained fashion. You have some restrictions on how you're supposed to do this. And namely, the restriction is that this conversion should be computable, right? So you convert IP to IQ in a computable manner. Right? And then what you do, really what we've shown through the diagrams that we've talked about, is you take that created instance of Q and you immediately feed it to the Q solver, right? So how does this sentence go? Convert, then feed IQ to the Q solver, right? This is what we did in the diagram. To the Q solver. And to create, right. And that creates a solver. Okay? And in particular, right, in mapping reductions, when you start with an arbitrary instance of the problem P, and you convert it to some particular instance of the problem Q in a computable manner, you immediately feed that to your Q solver, and then you just take the answer that your Q solver gave you, and you say, this is the answer of my P solver, right? So then, what I'd like to add is the answer of the Q solver is the answer of the P solver. Right, I'll draw the diagram in a second, but this is sort of in words what's going on. So this is the actual reduction that we're doing, right? This is the process by which we're creating a solver for P using a solver for Q, right? And some sort of computable instance modifier. Then what we need to do, really what we need to do in step 2 is we just have to show the correctness of this P solver, right? So that's what we're doing in step 2. It's not really, the fact that I'm showing that the answer to IP is the same as IQ, that's really just a proof of correctness of the P solver, right? So I'm going to show that the answer of the instance of the problem P is yes if and only if the answer to the instance of the problem Q is yes. But really why I'm doing this is because this is actually a proof of correctness. Proof of correctness for the P solver. And maybe it's not clear why this is a proof of correctness, but it will be clear once I sketch the diagram. Okay, so let me erase this part. Okay, so the diagram that we've seen several times now in this class when we've talked about mapping reductions is, you have this box here. This is fun when you do it on the blackboard. It's boring when you do it on the iPad. And the idea is you want to create a P solver, right? Right, you want to create a P solver using a Q solver, right? Because remember what we're doing is we're doing, let's write it here, P mapping reduces to Q, right? This is what we're trying to do. We're trying to create a P solver, right? So what does a P solver do? It takes some instance of the problem P, right? And then at the end, what it should do is it should spit out yes, right? It should return yes. It should return true when the answer to the instance of the problem P was initially yes, right? And it should return no. It should return no when the answer to the instance of the problem P was initially no, right? Because we're talking about a decider, really, when I'm talking about solvers here. In this case, and for this example, okay? So this is what the P solver should do, right? It should solve the decision problem P, right? So it should answer no when the answer is truly no, or sorry, it should return no when the answer is truly no, and it should return yes when the answer is truly yes, right? Now, how does it do this, right? How does it do this? Well, it first does step 1, right? So step 1, it takes IP, and it feeds it to our instance modifier, right? So this is my instance modifier, and the restriction on the instance modifier is that it should be computable, right? So it should have some Turing machine that implements it, right? Because the instance modifier is an algorithm, right? It's an algorithm which takes as input some input of type instance of the problem P, right? So here the input type is instance of the problem P. And now what it should return, its output type is, so its output type is an instance of the problem Q, right? And so it's working, this instance modifier is working for any IP, right? It's working for any IP, but when it takes this IP, it creates some particular IQ. Right, so this guy is particular, right? It's designed as a function of IP, right? So then when you take this IQ, right, which has been created from the instance modifier, and you feed it to the Q solver, in a mapping reduction, right, what the P solver should do is it should immediately take the answer of the Q solver. So suppose it says yes, right? So it should immediately take the answer of the Q solver and feed it to the yes of the P solver, right? So it's linking these two things together. I don't know if it's correct yet. Yes, that's step 2. But what it does in the actual construction of the solver is it links this yes from the Q solver to this yes from the P solver. Okay. And it does the same thing for the no answer, right? So if the Q solver returns no, then this no sort of feeds out to this no for the P solver. Okay? So this is the P solver designed as a function of the Q solver. Okay? And this is designed in a computable manner because everything here is computable. Everything here is computable. Yeah. Because I'm saying, if I could solve Q. Right? Okay, is this okay? Yeah, okay. So the one thing which I think students are confused by is, this step, right? So why is this step actually showing the correctness of the P solver, right? Well, what does correctness mean, right? What does correctness mean when you have a P solver, when you have a solver for a decision problem? Well, the correctness, right, so for this thing to be correct, when the answer of this is yes, the P solver should return yes, and when the answer of this is no, the P solver should return no. That's what it means for this solver to be correct, right? Well, if I'm able to prove 2, right, if I'm able to prove 2, then suppose my P solver told me yes, right? Suppose my P solver told me yes, then that must mean that my Q solver told me yes, right? But I'm assuming the Q solver is correct, right? I'm assuming the Q solver is correct, so that means that the answer to IQ was yes, right? So, let me use a different color. If my P solver returned yes, then that means that the Q solver returned yes, and because this is correct, that means that the answer to IQ is yes. But now because of 2, right, that means that the answer to IP was yes, right? So I can only get a yes, well, I get a yes if I have an answer of the instance of the problem P being yes. So now I also have to check for no, right? Because if my P solver tells me no, maybe it's also because the answer to IP was yes, which would be incorrect, right? So, so this is just by construction, and this is by step 2. So if I do the same thing for the no, right? So when I say I'm doing the same thing, I'm saying if my P solver told me no, I should guarantee that the sort of answer to the IP was truly no. So this is the return, right? I'm really trying to emphasize this point because it's important. This is the return of the solver, and now I'm trying to check that the return matches the actual answer, the answer that I know should be true, right? So if this P solver returned no, then that means that the Q solver returned no. But if the Q solver returned no, because I'm assuming it's correct, that means that the answer to IQ was no. But now by 2, right, by 2, this is an if and only if. So if I negate both sides, if I negate this answer IP being yes, that's just no. And if I negate this answer being yes, that's also no. So I get a no for a no. So that means that my answer to my instance of my problem P was also no. Okay? And so then what I showed is that my P solver, when it returns yes, it must mean that the answer to IP was indeed yes. And when my P solver returns no, the answer to IP was indeed no. Okay? So this is what we're doing in a mapping reduction, right? Hopefully that clarifies some things. Good. So that's great, right? Mapping reductions are great because they allow us to show many sort of results in terms of undecidability. Because notice, at this point, I've only talked about mapping reductions, right? So where does undecidability come in? Well, we've seen a few theorems, right? We've seen a few theorems, which I can write down here. Hello. So what have these theorems said? They've said, which side is the good side? I think it's this side. So these theorems have said that if I have P mapping reduces to Q, and Q is decidable, then this implies that P is decidable. Why is this true? Well, imagine I have P mapping reduces to Q, right? And I know that Q is decidable. That means that there's a Turing machine that decides it, and that halts on every input. So then just take that Turing machine and plug it into here, right? Then I have a Turing machine which decides the P problem, right? So this is true, right? And then I also have the result that if Q is C, or Turing recognizable, then I have that P is C. Why is this true? You can also verify this through this diagram, right? So now instead of a Turing machine which always halts and which accepts Q, you have a Turing machine which accepts Q but doesn't always halt when you have a no answer, right? So just take that Turing machine and plug it into the Q solver, right? Then if you have a yes answer for P, then the yes answer becomes a yes answer for Q. Then your solver here, which is the Turing machine that recognizes the language Q, will always say yes, right? So it'll always say yes if you have a yes as IQ, but that means you had a yes from IP. If you have a no from IQ, that means that, there's no guarantee, right? So maybe it loops, maybe it gets rejected, but that's okay because all you're looking for is a recognizer, not a decider. Okay? So if Q is C, then that means that P is C, because if Q is a recognizer, so if you plug in a recognizer here, then you also get a recognizer. So this whole thing, this whole box, becomes a recognizer for P. Okay? And the same argument can be made, so the same logic is if you had sort of a recognizer for the no instances, right? So if Q is co-C, then this implies that P is co-C. Okay? So mapping reductions are great because they allow you to preserve decidability and CE-ness from right to left, right? So that's great. And so where does undecidability come in? Well, it's just a contrapositive, right? So if I have these three statements, I can just take their contrapositive. Let's use orange. Hopefully it's visible. So what's a contrapositive? Well, so if P is not decidable, let me just write. P is undecidable. Ooh, nice orange. Then that means that Q is undecidable. And the same thing for, if P is not C, then that implies that Q is not C. And finally, if P is not co-C, this implies that Q is not co-C. Okay? So the contrapositive is in this nice bright orange. Okay? And so this is how you can argue, undecidability or not C, not co-C-ness. So hopefully this is what you're doing in assignment 6. There's no other way, so please do that. Okay, good. So that's great. Mapping reductions are great because they allow us to do this. The one problem with mapping reductions is that, remember the intuition that I was sort of giving you for P mapping reduces to Q? I was saying that it means that Q is at least as difficult as P, right? But it turns out this intuition kind of breaks in very simple cases. And so we're going to see that in a second, and we're going to see that Turing reductions allow you to fix this break of intuition. Okay, so let's see, what should I erase here? Okay, I think I'll erase this side of the board. Okay, so everyone's written this down? Yeah, I think so. All right, so let's look at an example where there's a break in our intuition. So consider the following example, where I ask you, although you probably know the question, given that I premised the example with a break in intuition. So is there a mapping reduction such that the not halting problem mapping reduces to the halting problem? Okay, so now I'm going to venture a question to the class, and I don't want to take the answer from the people who immediately know it. So let's see. Take 15 seconds to think about this while I drink some tea. Yes, I know you know. I want someone else to know. Oh, Dashiell looks sad, so. Okay, I've counted to 12. Okay. Angela? No? Okay. It's okay. Sorry to put you on the spot. Hey? It's no? Great, why? Okay, you sensed it. Great. That's the right answer, though. Sienna, maybe you can complete the right answer. Yeah, I think that's right. I didn't quite hear the entire answer, but yes, that's true, right? Because the halting problem, I think, yeah, that's absolutely right, actually. The halting problem is CE, right? So you can check yes answers. But it's not co-CE, right? It's not co-CE. Because if the halting problem was both CE and co-CE, then it would be decidable, right? Which is not, right? So the not halting problem, on the other hand, you can check, let's see, no answers to the not halting problem, because what is the not halting problem? The not halting problem asks, does M not halt on X, right? So does M loop on X? Well, you can't check a yes answer, but you can check a no answer, right? Because a no answer to the not halting problem is M halts on X, right? And you can check M halts on X, just run M on X, right? So this is co-CE, but it's not CE. And so then you have a contradiction, right? Because mapping reductions tell us that CE-ness is preserved from right to left, but here I have that this is not CE, and this is CE, right? So this is absolutely very good, Angela and Sienna. No. Okay, so this is no. But this, give me a second, but this is a bit counterintuitive, right? Because it kind of doesn't quite match our intuition. Because if we look at these two problems, right, if we look at these two problems, it's surprising, at least to me, that you can't find a mapping reduction here. Because clearly, the halting problem is at least as difficult as a not halting problem. If I can solve this, right, if I can check that some Turing machine halts on X, then of course I can check that it doesn't, right? Just flip the answer, right? But you're not allowed to flip the answer in mapping reductions, right? In mapping reductions, the only thing you're allowed to do is, instance modify IP to IQ, then feed that to the Q solver, and then immediately extract the answers from the Q solver. So there's no flipping of answers or processing of answers allowed, right? And so that's what causes this intuition to break down. So what I'd like to say then is that intuition, right? Where is this? Intuition of, quote, at least as difficult breaks down okay, and so that's not good, so we're sad. Let's put a sad face. Intuition breaks down. And so what's the solution? The solution is Turing reductions. So Turing reductions are going to fix this break in intuition, and they're also going to allow us to see something very cool if we have the time to do so. I think we do, because I'm on time. Okay, so now we can talk about Turing reductions briefly. Theo, you had a question? How do you mean does the same thing? Like, yeah, absolutely, yeah. There's breaks in intuition at that level as well. Yeah, so Turing reductions fix that, but it's much harder to visualize how they fix that because there's sort of this hierarchy that I'm not going to have time to present. Okay. Any other questions? Yeah? Oh. Mm-hmm. Complement? Complement, not conjugate. That's much more complicated. Yeah. So that's not true if the problems are decidable. But yeah, if you have a CE and a co-CE problem, then yeah, there's no mapping reduction. Yeah, very good. Okay, so we can now talk about Turing reductions. Let's see. I think what I'll do is I'll still keep this because I can contrast it. Oh no, I guess not. Okay, I'll just erase everything. Okay, let's erase everything. Okay. I guess, yeah. right. Okay, good. So Turing reductions, what are these reductions? So Turing reductions, like I talked about last Tuesday, were introduced by Emil Post, who called them Turing reductions for the simple reason that Turing had thought about this thing called the oracle. And he had sort of talked about an oracle Turing machine, which we'll define in a few minutes, in his PhD thesis. But he had talked about it like as an aside in a very small paragraph, and no one really paid attention to it until Emil Post. And then Emil Post was like, oh, you can use this for something. And then he made a whole theory out of it and still called it Turing reductions. So that's how generous Emil Post was. Okay, so what are Turing reductions? So in Turing reductions, and now please be careful when I speak, because I think what I might do at some point is I might say mapping reduction, even though I mean Turing reduction. So if I do that, then it's probably a mistake. Okay, so Turing reductions are, given two decision problems, P and Q. We write that P Turing reduces to Q, and so that's why we use a T. And to show this, it's the same intuition that we say that, Q is at least as difficult as P, or solving Q is enough for solving P, but at this point, this intuition always really holds, okay? So to do this, there are two steps, like in mapping reductions. The first step is very similar to the first step of mapping reductions. So it's to convert some arbitrary instance of the problem P to some particular instance of the problem Q, particular meaning that, IQ is designed as a function of IP. Okay? And so what I'm going to do is I'm going to take IQ and use the Q solver. So I'll use the Q solver, which is also called, and so I will start calling it this, the oracle for Q. So, the Q solver is also sometimes called the oracle for Q. And you can use this Q solver in any computable way. So in any computable way. So now it's not just that, you take IQ and you immediately feed it to the Q solver. You can take IQ and you can sort of do some manipulations, anything that's implementable with a Turing machine, or, just some algorithm, and then feed it to the Q solver maybe once, maybe twice, maybe 3 times, and then post-process, and then maybe feed it to the Q solver again. So you can do whatever you want with the Q solver as long as it's computable. Okay? So in any computable way, so, for example, use the Q solver 10 times if you fancy using it 10 times, or maybe flipping the answers, and so on. Okay. So you do this to eventually create, right? To create a Q solver. No. A P solver, yes. Okay, so this is the first step. So this is very similar to the step in mapping reductions, which makes sense because Turing reductions and mapping reductions are reductions, right? The only difference is now you can use the Q solver or the oracle for Q in any way, any computable fashion. Okay? So that's step 1. And then step 2 is proving the correctness of your P solver. So exactly the same thing as the step 2 for the mapping reductions, except that now, because you can do any type of manipulation with your Q solver, it's no longer as easy as saying that, the answer to IP maps to the answer of IQ all the time. Right? That's not enough, because maybe you can flip an answer, maybe you can post-process, so you have to keep track of what the P solver is doing. And so step 2 is a proof of correctness in general. And so in general, proofs of correctness for decision problems are sort of the following. If you have that the answer, if you know that a priori the answer of the instance of the problem P is yes, then what you must show is you must show that the P solver returns yes. Okay? So this is the first sort of subpart of 2. And the second subpart is if the answer of the instance of the problem P is no, then you must show that the P solver returns no. Okay. This is what you do in a proof of correctness for an algorithm that, works for a decision problem. Right? It makes sense because, you only have two types, two values in the return value set. And so you just have to show that if the p-solver returns yes, then it also means that the answer was a priori yes, and the same thing for no. So there is a mapping really between yes and yes, but now it's slightly more involved. You can't really just say it's because there's a mapping between IP and IQ, because you can flip and do other things, right? So you have to keep track of what the p-solver is doing. Okay, so I think to illustrate this, I'm going to give you an example, and the example is going to fix our previous example. So it's a fixing example. Okay. So in this example, I want to show that the not halting problem Turing reduces to the halting problem. Okay. So before I do it, let's just think about intuitively how this should work. So, in a Turing reduction, it's the same idea as in a mapping reduction. Suppose you have an HP solver, right? So you have an HP solver, and it's solving the halting problem, right? So when you give it some Turing machine and some input string x, it says yes when m halts on x, and it says no when it doesn't. So then, what you could do to then solve the not halting problem is you could say, well, when the halting problem solver says yes, then return no, and when the halting problem returns no, then return yes. That's it. So let's just do that. Okay, so I'm going to create a not halting problem solver. So this is going to be my not halting problem solver. Okay, so how is this going to work? Well, it's going to take some instance of the not halting problem, which in this case is some Turing machine m and some input string x encoded in, let's say, binary. And what the not halting problem solver should do is it should return yes. It should return yes when the answer to the not halting problem is yes, so m does not halt on x. And it should return no when the answer is no, so when m does not halt. No, wait. It should return when the answer to the not halting problem is no. Okay, so this is the outside, right? This is what we should do on the outside. Now, how do we actually do this? So we need an instance modifier. So that's, step one, right? That's part of step one. So how is this going to work? So I take the not halting problem instance, and I feed it into my instance modifier. Okay. And now, what I'm simply going to do is I'm just going to copy, right? I'm going to copy this code, this string, to the instance of the halting problem. Okay, I'll just copy it. Right? So the instance modifier is just a copy function. So it's a copy function, which is computable because we showed in class that you can copy strings. Okay, so I take this mx, right? This mx, and I just copy it over to my instance of my halting problem. So that remains mx. Okay. Okay. So far so good. So now, I take the mx, the machine m and the input string x encoded in binary, and now I feed this to the HP solver, which I should probably start calling the oracle. So this is also called the oracle for the halting problem. Okay. Right, so I do this, and now what should I do? Well, now if the halting problem solver or the oracle for the halting problem returns yes, so if this returns yes, then I should add an extra step here where the only thing I do is I flip the answer. Right? And I can flip answers, right? That's very computable. You say, well, if you go to an accept, then just go to a reject. If you go to a reject, just go to an accept. Computable. So I flip the answer, and this becomes a no. Becomes a no. And what I do is I feed this no into what should be the no for the not HP solver. Right? So now this is not aligned. Okay, now it is. Okay. So the no, this yes becomes a no, and then it feeds to this no for the not HP solver. And then the same thing for the no here. So if the halting problem, the oracle for the halting problem returns no, then I flip here, and then I get a yes, and then this yes carries out to this yes here. Okay? And this is my construction for the not halting problem solver, which is also sometimes called, so this is a bit confusing, this terminology, but we sometimes call it an oracle Turing machine. So an oracle Turing machine is a Turing machine with an oracle, so with some solver, with oracle for the halting problem. Let me just do the proof of correctness, and then I'll get to your answer. Okay, so this is the construction. Oh, hello. So this is the construction, right? Now what we need to do is we need to show that, you know, the not halting problem solver is correct, that it does solve the not halting problem. Okay? So hopefully I don't get these double negatives backwards, but let's do this. Okay? So, you know, I need to do this then, right? So what I need to do is I need to show that if a priori I knew that the answer to the instance of the not halting problem was yes, then the P solver, the not halting problem solver returns yes, and the same thing for no. Okay, so this is what I need to do. So let's do that. Okay, I gotta say this chalk is really good. Like it's not a myth. It's very nice. Okay. Anyways. Okay. So suppose, right? So this is the proof of correctness. So proof of correctness. So proof of correctness for, I guess, the not halting problem solved. Okay. So I think I'll only do it for yes because it's going to be exactly the same argument for no. So, you know, suppose the answer to the instance of the not halting problem was yes. Right? Well, what does that mean, right? The not halting problem asks, does M not halt on X? Right? So this is, does M not halt on X? Okay, or in other words, does M loop on X? Right? So now, suppose this was yes. Suppose I had an instance that was yes. Then what should happen is my not halting problem solver should return yes. Right? So let's see if it does that. So if the answer is yes here, that means that it's true that M doesn't halt on X. So that means that M loops on X. So that means that M loops on X. Okay, so I have that M loops on X. So now what happens, right? I have this M that's looping on X, right? And, you know, I know this a priori because I'm just doing this by assumption, right? And I encode this in binary, and I copy it using my instance modifier. I copy it over to my instance of the halting problem, and now I give it to the halting problem solver, okay? So I give it to the halting problem solver, but by assumption, I know that M loops on X, right? I know that M loops on X. So what should the halting problem solver say? It should say no, yes, right? Because the halting problem is, does M halt on X? In this case, the answer is no. M loops on X, right? So the halting problem solver should return no. Okay, so the answer, right, so the halting problem solver says no. Wait, says no, yes. Says no. And then what happens is, you know, at this point I have a no. Now what happens is this no gets flipped and becomes a yes, right? So the answer gets flipped to a yes. Flipped to a yes. And then this yes is sort of just propagated outwards to this yes for the not halting problem solver, which means that the not halting problem solver, so the not halting problem solver returns yes, which is great. So that's nice. Okay. And then the argument would be exactly the same, so I won't write it, but it's the same argument for the answer to the not halting problem being, by assumption, no. Okay. So then I have a solver, right? I have a solver for the not halting problem. That works. which is great, right? That's great. And so that tells me that the not halting problem, Turing reduces to the halting problem. So now I can put a nice box. Okay. Yes, Owen. Yes. Oh, the oracle is just a special name for the HP solver, which is really the same thing as when we had mapping reductions, right? No. What is it? No. So what do you do in a reduction, right? In a reduction? Okay, so this is a good question. Owen asks, doesn't this require us to solve the, would you say, halting problem, right? So I'm gonna morph the question, right? Because what you're doing is a reduction, right? In a reduction, all you're doing is you're showing that if you can solve this, right, then you can solve this. But how do you show this if then, right? You assume the if, right? So technically yes, but really no, because what you're doing is you're doing a reduction. You're not talking about undecidability or decidability yet. So I think it's really important to sort of create sort of a line between these two, because you can always, right? You can always do reductions for different problems if there's a reduction for them, right? But then talking about the decidability, undecidability, that comes after. Right? So that's why I think it's really important to first deal with the reduction, first deal with, showing that solving this is sufficient for solving that, and then after that talking about undecidability, which we'll do in a second. Yeah? Yeah. 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 But it's the same solver when you were to do a mapping reduction, right? So maybe I think you're sort of jumping the gun a bit, because what we'll show in a second is we'll show that if this were undecidable, then this would also be undecidable, or if this is decidable, then so is this, right? So the idea of Turing reductions, right, is they allow you to show undecidability, like you just said, because if you know that, if we had swapped this and we had the halting problem, Turing reduces to the not halting problem, which would be the same process, right? Then you know that the halting problem is undecidable, so then you know that the not halting problem is also undecidable. But the actual point of Turing reductions is that they allow you to create sort of relative classes, right? Classes which are relative to each other in terms of impossibility, right? So what we'll see in a second is we'll see that these two problems are sort of equivalent in terms of impossibility, right? So I agree with you that it's impossible to do this, but suppose for a second, imagine that it was, then it would be possible to do this, right? So this is what we're doing, right? Dashiell. Yeah. Very good. Yes. Very good. Excellent. Very good point, actually. Yes. Very good. Excellent. So when you have Turing reductions, you lose the power of the C-ness or the co-C-ness, but in return you get something very special, which I'd like to get the time to do, so I need to limit questions. But yes, that's a good point. Quickly, Tiffany. Quickly. Yeah. It's a contrapositive. So yeah. I guess not quite, but yes, not quite, but yes, you can go the other way. So not for the reason I give you, but yes, you can go the other way. Yeah. Okay, good. So now what I'd like to do is I'd like to rush through these definitions because I want to get to something cool. So this is the example I'll give you for Turing reductions. Now what I want to do is I want to formally define these things. So let's do that on the left here. So to properly define Turing reductions, we need to properly define Oracle Turing machines. And Oracle Turing machines are not very complicated. They're like Turing machines, except that they have some Oracle. Okay, so let's define that. Suppose I have some non-empty alphabet, some decision problem A, and some language corresponding to this decision problem, which is just a subset of sigma star. Okay, then an oracle Turing machine is, oh, I guess let's denote it M superscript A. So it is a Turing machine which can query in any computable manner an oracle for A, which is also sometimes called, which we've been calling, not sometimes, which we've been calling an A solver. Okay. So this is what a oracle Turing machine, M superscript A, is. And so then maybe quickly I can define what an oracle is, but hopefully the intuition is already there. So an oracle for, let's say, the decision problem A does the following. Given some string in sigma star, OA decides, so it makes a decision in finite time if X is in L sub A, right? So it does this in finite time. Okay? So this is what an oracle Turing machine is, M superscript A. So you might think at this point that this is a bit silly because, for example, if you're given some decision problem A, right, then the oracle Turing machine with oracle A, well, it decides A in, one step, really, right? It does, so the given the decision problem A, M superscript A decides A in quote-unquote one step. How does it do that? Well, you set up the vanilla Turing machine, the architecture of the vanilla Turing machine, and then you just go to the oracle for A and you ask, is my input string in A? And it's supposed to tell you in finite time, right? So then, the only step in this Turing machine would be, so M superscript A would be, on input W, query the oracle for A, and return its answer. So it's a bit silly, but it's defined for a particular reason, and it's defined because you can now talk about sort of relative impossibilities, right? So if something were possible, then maybe something else is also possible, and that allows you to create sort of classes of problems which are impossible but allow you to be sort of more and more impossible. So you get classes of more and more impossible problems. But before we get to that, the last thing I want to say is that really oracle Turing machines can also be seen as a generalization of Turing machines. So how does that work? So let the decision problem denoted by the empty set be the decision problem with answer always no. Oops. Right? So this is the empty set, but I'm sort of overloading notation as I do in this class often. In this case, I'm saying that the empty set decision problem is the decision problem where the answer is always no, right? So in other words, L sub the empty set, right? L sub this decision problem. So this is a real overloaded notation, is the empty set for meaning the sort of the empty language, okay? So of course the answer is always no, because is there any string in the empty set? No, it's empty, right? So what's the point here? The point is that if I'm given, right, so the point is that given some Turing machine M, the oracle Turing machine, so the oracle Turing machine M superscript the empty set, so the oracle Turing machine which has oracle, the oracle for the empty problem is equivalent, well, I guess, So the oracle Turing machine M, the empty set, where it's the Turing machine M, so this same Turing machine, plus the oracle for the empty set is equivalent to M, right? So it's equivalent to M. So what I'm saying is that if I have a Turing machine, then this is also actually just an oracle Turing machine with oracle the empty set. Why is this true? Because just copy the code of M to M superscript the empty set, and then you can sort of query the empty set solver, but it'll always tell you no, so you don't sort of gain anything. So the point I'm making is that Turing machines, so oracle Turing machines, are just sort of a generalization of vanilla Turing machines. Okay. Yes? Yes? Oh, some of my words are hard to understand? I know, man, tough. No, okay. Decision problem A, L sub A. An oracle Turing machine, M superscript A, is a Turing machine which can query in any computable manner. Oh, I see. Oh, it's illegible because it's not grammatical. An oracle for A, the A solver. And so what is the A solver? Given any string in sigma star, the oracle for A decides whether X is in L sub A in finite time. Okay. And this is just saying that M superscript A decides the decision problem A in one step. So on input W, it queries the oracle for A and it returns the answer. Yeah? Yeah, it allows you to query this oracle, this solver, in any computable manner. Let's see, Louis has his hand up, so that means I have a mistake somewhere. Yeah. Yeah, of course. Yeah, it seems stupid. Yeah, I agree with you. We'll get to it in a second. That's why I'm rushing, because I need to get through these definitions to get to the point. Yeah, I agree with you. It seems silly at the moment. Okay. So, but there's a good point for this. There's a good point for this, and it's that it allows us to, first of all, define formally a Turing reduction. So let's define that formally here. So I'm going to erase this. I'm going to erase my illegible handwriting. Okay. Okay. So again, oracle Turing machine, not that special. It's like a Turing machine, right? So imagine the control unit and every sort of gizmo we added in the sort of 9-tuple definition for a Turing machine, except that now you can query oracle, right? Solver, right? Some magical box, okay? But the point of this is that it allows us to formally define a Turing reduction. So that's what I'm going to do here. So given, okay, so let's try my hardest to make this legible. Given decision problems P and Q, we say that P Turing reduces to Q. So P Turing reduces to Q. If there exists some oracle Turing machine with oracle for Q, so some Turing machine, some algorithm which has access to an oracle for Q or a Q solver, right? So if there exists some Turing machine Q which decides the decision problem P. Right, and so remember, this is a key word, decides. Decides just means that it halts on every input. So decides means it halts on every input. And it always gives the correct answer, right? Well, of course, yeah. And it gives the correct yes or no answer. Okay. The other way of saying this, right? The other way of saying this is that we say that P, right? P is decidable relative to Q. Okay? So meaning that, if Q is decidable, then P should be decidable. And we'll see that in the theorem, but the term we say is that P is decidable relative to Q. Okay? So this is the formal definition of a Turing reduction, and Turing reductions are really the most general form of computable reductions. So they actually include mapping reductions. So a mapping reduction really is a Turing reduction, but just with additional constraints. And polynomial reductions, which you've seen in 360 and which I'm sure you enjoy even more than my type of reductions, are also Turing reductions, but they have additional constraints on the types of resources you can use in the instance modifier. So now, what's the connection between Turing reductions and undecidability? So the connection to undecidability. So this connection is stated in the following theorem, which says that if A Turing reduces to B and B is decidable, then A is also decidable. Okay? So this is sort of a fundamental theorem in Turing reductions. And so it says that decidability is preserved from right to left. Okay, so this is why we have this other technical term that P is decidable relative to Q. Okay? And I can prove this. I think, fairly quickly if I sketch a diagram. So suppose I have that that A Turing reduces to B. So what does that mean? That means that I have some A solver, right? I have some A solver. And how does the A solver works? Well, it takes an instance of A, and then some code executes, right? So imagine this is just some block of code. And in this block of code, you can query the oracle for B any number of times, right? So you query here, you query the oracle for B. You query the oracle for B. And then the oracle for B in finite time tells you yes or no. Okay, this is not query, like a query, but query. Okay? Okay, so, and then, then you get a yes here or a no here, and this creates an A solver, right? So this is what it means for A to Turing reduce to B, right? Now, suppose that B is decidable now, because this is the other part of the assumption. Suppose that B is decidable. If B is decidable, that means that there's a Turing machine, right? There's a Turing machine which decides it. So there exists some Turing machine M prime which decides B. Okay? So then what I can do, I can sort of observe that if this is true, then I don't actually need this oracle for B, right? This oracle for B isn't really helping. I could just use the Turing machine M prime because it serves exactly the same purpose, right? So then what I can say is I can say, well, let's just replace the oracle for B with M prime, right? And now what I have is I have some code which is computable, and this code which is computable is querying some other code which is computable, right? So altogether I have, something that's computable, which is computing in finite time the answer for A and giving the correct answer, yes or no. So that means that I have some computable manner, some computable manner of deciding A, right? So this tells me, so then therefore, so then let's call this a new, this can become the A prime solver. So therefore the A prime solver is a Turing machine, so not an oracle Turing machine, just a vanilla Turing machine, which decides A. And so that means that A is decidable, so that proves the theorem. Okay? Okay? So all this is saying is that Turing reductions preserve decidability from right to left. And so that's why there's this additional term here that if P Turing reduces to Q, then P is decidable relative to Q. Right? So if Q is decidable, then P should also be decidable. And so if you use the contrapositive, then of course, if P is undecidable, then Q should be undecidable. So the contrapositive of the theorem tells us that undecidability holds from left to right, and decidability holds from, is preserved from right to left. Okay? The one thing, of course, is that Turing reductions don't allow you to preserve CE-ness or co-CE-ness, like we saw in the previous example with the halting and the not halting problem. But the payoff is quite nice because they allow us to talk about degrees of impossibility. So, yes, Dashio. Yeah. That's, if A is decidable, yeah, absolutely. Yeah. Because B could be as hard as you want, or it could be decidable. Yeah. Very good. I'm going to erase this too. Okay. Okay. No one cares. So I'll erase it. Okay. Sorry, I'm going a bit fast because this last part is sort of the culmination of the whole class, so it's very important. Okay. Okay, so because if you remember during lecture 1, where I was very excited and happy to be here, I'm still very excited and happy to be here, I had talked about this sort of infinite sequence of more and more impossible problems. And Turing reductions really allow us to talk about this. So that's what we're going to do in the final 14 minutes. Damn, 14 minutes of the class. So let's define something which is going to allow us to do this. So we're going to create classes of decision problems. To do that, probably a good thing to create an equivalence relation. So we're going to create an equivalence relation using Turing reductions. So suppose I have decision problems A and B. I say that A is Turing equivalent, so it's Turing equivalent to B, which is written A Turing equivalent to B. If A Turing reduces to B and B Turing reduces to A, right? So what this is saying is, if you can solve B, then you can also solve A, and if you can solve A, then you can also solve B, so these two things are equivalent. So really you can just think of this as, A and B are at the same level of possibility, or really, because there's only one level of possibility, impossibility. Okay, nice. All right. So I won't prove this, but note that the Turing equivalence is an equivalence relation. The reflexive and symmetric property are trivial. The transitive one is slightly less trivial, but it's the same argument as when we talked about mapping reductions being transitive, so you can compose oracle Turing machines, and you still get an oracle Turing machine. So this thing is an equivalence relation. Excellent. That's what I was looking for. So that means that I can create equivalence classes. Right? So equivalence classes based on this equivalence relation. So an equivalence class, so, given some decision problem A, an equivalence class, so EQ for equivalence class of A for the Turing equivalent relation is called quite fitting, it's called a Turing degree. A Turing degree. Very nice. Thank you, Emil Post. A Turing degree. And so the intuition of a Turing degree is that degree, right, is sort of the level at which you are, right? So if you're at some degree, then this is the level of impossibility that you're at. This is the intuition, right? So how do we talk about this formally? An equivalence class is then denoted by the degree of A being the set of all decision problems B such that A is Turing equivalent to B. And so the reason why we're not doing this with mapping reductions is because under mapping reductions, you couldn't have that if you had a C and a co-C problem, which was just their complements, so the halting and the not halting problem, then these two things wouldn't have the same degree of impossibility. But that's counterintuitive, right? Because the halting problem, not halting problem sounds like it should be at the same level of not being possible, right? And so Turing reductions and then Turing degrees induced by Turing reductions allow you to do this. And so the idea now is you have degrees, right? So think of them as just numbers. You have some degree for some level of impossibility, then you go up a degree, so you go up a level of hardness and possibility. And so this creates an order, right? A partial order. So you can create a partial order on Turing degrees, where you say that, you know, the degree of A, so the degree of A, which is often sort of denoted as a lowercase a but bolded, so I'll do this, is less than or equal to the degree of B, so some other decision problem B, which I'll lowercase with a B and I'll bold. Maybe I should just use a different color. Anyways. So this is the partial order I'm defining, and I'm defining it by saying that this is true if and only if A Turing reduces to B. Okay? So this is my partial order, and so this is what it means for the degree of B to be less than or equal to the degree of A to be less than or equal to the degree of B, or A to be less than or equal to B. So, you know, this level of impossibility is at most this level of impossibility. But you can also create like strict inequalities, right? So strict inequalities, which I'll define over there. So strict inequalities are useful because I'll use them in my last definition. So we would say that, you know, A is strictly less than B, if and only if A Turing reduces to B, but B does not Turing reduce to A. Okay? So this is what strict inequality is in this partial order. So you can think of, you know, you have two levels of impossibility. You know, this is the degree of this level of impossibility. Then you have some other level of impossibility. And so this one is strictly more possible than this one if you can never sort of Turing reduce from B to A, but you can always from A to B. Okay? So this sort of preserves our intuition of order. Okay? So finally, I'm able to talk about what I've been wanting to talk about for the last 26 lectures, which is that Turing degrees and this partial order. So this partial order creates a chain of strictly more impossible. Well, let's say strictly more impossible classes of problems. Okay, so how do I do that? Like, how do I actually create this chain of impossibility in 7 minutes? So if I have a chain of sort of more and more impossible classes of problems, well, I have to start at some point in the chain, right? I have to start at the beginning of the chain. So what's the beginning of the chain? Naturally, that's the classes of problems which are decidable, right? So, you know, if I have some chain, right, if I have some chain of more and more impossible problems, then this first degree should denote the degree of decidable problems. And it turns out I won't prove this because I have 7 minutes, but I'll leave it as an exercise. Any pair of decidable problems are Turing equivalent. So I'll leave this as an exercise. It's a very fun exercise. Why else would I give you an exercise? Not because I'm running out of time. So any pair of decidable problems are Turing equivalent. So that means that if I create the class of decidable problems, then I can use any decidable problem as a representative. Right? So then here, for the first level of impossibility, for the first degree in this chain, I'll just say, well, let's take the degree of the empty set decision problem. Because the empty set decision problem is Turing equivalent to all other. And so the idea is that this Turing degree creates the class of, so this is the class of decidable problems. Okay, so I'm here. Now, the question is, how do I go up the chain, right? Because I'm claiming that I have a chain of more and more impossible problems. How does this chain actually occur? Well, unsurprisingly, hopefully, it occurs via the halting problem, but a generalization of the halting problem. So there's no escaping the halting problem. How much time do I have? Oh, 4 minutes. Great. Okay. I was supposed to end 15 minutes ago, but whatever. Okay. So the last thing I'll say, right? The last thing I'll say is we can define, so given some decision problem A, we need to sort of define a way to sort of jump up this level of impossibility. And so to do that, we create the jump operator. So the jump operator, so jump of A, which is also sometimes denoted A prime, is just a generalization of the halting problem. And so is the jump of A is the decision problem, such that L sub A prime is the collection of binary encodings, right, of oracle Turing machines with oracle for A. So this isn't any Turing machine, it's an oracle Turing machine with an A solver, right? And this A solver comes from this decision problem A. So that's how I'm sort of jumping up a level. I have the decision problem, and now I'm going to create the sort of generalization of the halting problem with A. So I take an oracle Turing machine with oracle A and some input string X. So you know MA is an oracle Turing machine. And the sort of necessary and sufficient condition here is that MA halts on X. So this is the decision problem A prime. It's just sort of a generalization of the halting problem using oracle Turing machines. Okay? And so it turns out, I also don't have time to prove this because I have 2 minutes. It turns out that the degree of A, so the degree of A, is strictly less than the degree of A prime, which hopefully isn't all that surprising, okay? Because if you have A being the empty set, right? A being the decision problem of the empty set, what is A prime? Well, A prime is the empty set prime. So what is the empty set prime? It's a decision problem. So it's a decision problem that asks, is an oracle Turing machine with oracle the empty set halting on some input string? But an oracle Turing machine with oracle the empty set is what? Yeah. Yeah. Excellent. Very good. Because M superscript the empty set is just some vanilla Turing machine. And so the empty set prime, well, this is just the halting problem. Fantastic. Right? So it's true for this, and so you can generalize this argument using a more general sort of diagonalization argument that Prakash gave. Okay. So why am I talking about this? Because now, if I go back here, if I go back to this chain of more and more impossible problems I wanted to create, so this was the first degree, this was the first level of impossibility. In fact, this is the only level of possibility, which you can just denote as 0. Then you can go up a level by jumping, right? So you jump, you take the degree of the empty set prime, so this is 0 prime. And so you have a strict inequality by the previous theorem. And so what you can do now is you can just apply the jump again, right? So you apply the jump again. So you get the class of decision problems with representative, the jump of the empty set, right? So you have the empty set prime prime, which is also just denoted 0 prime prime. Okay? And this keeps on going, right? This keeps on going. So you get a chain of more and more impossible. Okay? So how much time? Oh, okay, I'm on time. Okay. And so the last thing I want to say is this is awesome, right? Because this tells us that there's more and more impossible problems, not something that you could easily think of. And the one other interesting thing is that all of the CE problems that we've seen, all of the CE problems, it turns out have degree at most 0 prime. So 0 prime is kind of like an upper bound in terms of CE-ness. There are problems which are not CE which have degree less than 0 prime, unintuitively. But 0 prime is sort of the threshold of impossibility where you can at least check things, right? Beyond this, we're sort of like hopeless. Okay, that's it. So I think there's calculus people that want to come in, but maybe if you don't mind, so people who want to leave, please leave, but I'd like to take a picture with everyone. Maybe Ian can do that. So I had a speech to tell you, but I think I'll save it for the review session. Okay.